Okay, so today what we want to talk about is Ampere's law applying to magnetic fields to a long straight wire. So a dude named Ampere, he was studying magnetic fields. Remember that the last time we talked about Ørsted, who discovered that there was this relationship between magnetism and electricity because he flipped the switch in his circuit, the compass needles on his lab table moved, and so he could see that relationship. Well, once that got out into the scientific community and people started studying this, Ampere started quantifying this, and he found that the magnitude of the magnetic field near a long straight wire is directly proportional to the current in the wire. So if I run a stronger current through here, there will be a stronger magnetic field out in this area around the wire. And remember that this is the way we would write that is the magnetic field is symbolized by that B, and the I is going to be our current, and then alpha is that proportionality. So the next thing then he said is, but as you get further and further and further away from the wire, that magnetic field drops off inversely. And so it gets smaller and smaller and smaller and smaller the farther away you get. And that's really, again, where we have this B is proportional to 1 over the R, and we 1 over R, and that's an inverse relationship. So putting that together, he ends up saying that the magnetic field is proportional to I over R. Now, how do we turn that into an equation? Remember, we would add some kind of a constant. So in order to make this an equation, we multiply by a proportionality constant, which is going to be K. And it just so happens that that K value is mu naught over 2 pi. So if you remember mu naught, this shows up over and over again in electricity. Way back when we started static electricity, remember we said that there's this KQQ over R squared? Well, originally they thought that was like the fundamental constant, and later we come to find out that it's this mu naught that's embedded into all of the different magnetism and electricity. So this is the value of that mu naught. It's 4 times pi times 10 to the negative 7, which ends up being like 12 point something, 12.43 or something like that, times 10 to the negative 7. So watch how you put that in your calculator. When you put that in, you're going to want to multiply these first and then parentheses the whole thing for that. So we end up with Ampere's law, which says that the magnetic field is proportional to that constant times the current divided by 2 pi r. Now notice that this 2 pi r should look familiar to you because that's the circumference of a circle. So what it's really saying is, as I take this magnetic field, that magnetic field is being distributed around this the surface area or the circumference of that circle. And so the bigger that circumference becomes, the more you're spreading that out. Another way to think of it would be like a flashlight. If you take a flashlight and you turn the flashlight on and you bring it right up against the wall and you shine it right onto the wall there, then you'll see a really dark or a really bright, intense spot. But as you pull the flashlight away from the wall, you'll notice that all of that light is getting spread out over more and more and more area. And that's kind of the same thing that's happening here. You have that magnetic field that's getting spread out over more and more and more of that same area, or of a bigger area. And so in general, the most general form is that we would simplify this into the mu naught times I divided by the length that it's being spread out over. We're not going to deal with that one. We're only going to deal with this mu naught I over 2 pi r, and that's the way it's going to be. So Ampere's law then became the direct application for what we would call now a solenoid. So if I take a wire and I say, hey, if I have this wire here and the current is going this way in it, then there's a magnetic field around the wire that if I were to start looping the wire and come up with this whole bunch of, I can't even do it with this wire here. If I come up with this where there are a whole bunch of loops, that's what we would call a solenoid. So here I have this, you can see there are a ton of different terms on this. And all it is it's a hollow on the inside and a whole bunch of wires wrapped around the outside. And you can see where my 2 end connectors are for the solenoid. So a solenoid can be considered a set of circular loops that are placed side by side, all carrying the same current. And you had to do that with your speaker or with your wind turbine. If you were making either one of those projects, you were making solenoids, basically. It produces a uniform magnetic field inside it, and this can be placed into Ampere's law using that equation. So if we take the number of loops, which is your n value, times that constant mu naught, times the current that's running through it, and that will be then the length of the solenoid. So how long is the solenoid? So if I take and measure it from here to here, how long is that? That's going to be the L value that goes in there. And that's the second equation that we'll look at, is those two different equations. The one for a long straight wire and the one for a solenoid. So how do you know whenever you're in Buzz and you're doing the problems? Well, you just look at the problem. Like if it says that it's a long straight wire, you're going to use mu naught I over 2 pi r. And if it says that it's a bunch of coils or a bunch of wraps or a bunch of turns or a solenoid, then you know that it's going to be this N times mu naught I over L. So sample problem, a vertical electric wire in the wall of a building carries a current of 22 amps upward. So here's my vertical electric wire, 22 amps upward. What is the magnetic field at a point that is 5 centimeters away from this wire? So because this is a vertical electric field, I'm going to end up using that mu naught I over 2 pi r. So here is the mu naught, 4 pi times 10 to the negative 7. The current, they tell us, is the 22 amps. And then I have 2 times pi, and this is 5 centimeters is my radius, but remember it's in centimeters, so I have to convert that. And I end up with a magnetic field here of 8.8 times 10 to the negative 5th Teslas. And that is going to be the magnetic field there. Now, if you remember in the last video, we talked about the first right-hand rule, which we are going to practice a little bit more tomorrow. And in that first right-hand rule, we talked about a charge that's being shot into a magnetic field. So we used our fingers field, thumb velocity, palm force, fingers field, thumb velocity, palm force, like you're pushing on it or someone's pushing on you. Well, in the second right-hand rule, it is way, way, way easier. So I have this wire, and if the current is going towards the ceiling, so the electrons are all moving towards the ceiling, which means I'm still going to take the direction of the electrons, which is my thumb, and point it towards the ceiling. My fingers are still going to be the direction of the magnetic field, but what happens then is if I grab the wire in the direction that the current's going, then my fingers tell me the direction that the magnetic field is going around that wire. So if you notice on the picture here, the current is going towards the ceiling. If I grab the wire with my thumb going towards the ceiling, then my fingers will curl in that counterclockwise direction, and that's the direction that the magnetic field will go around that wire. Notice then that the only other option is if the current is going down towards the floor, I would grab the wire the opposite way and my fingers curl in the direction that would be in a counterclockwise direction. So those are the only two options. The tricky part then just gets to being describing it. So if my wire goes this way and I say, hey, the current is going that way, then I'm going to grab my wire this way. And the question might say, well, what direction is the field at this point over here? And I would have to say that it is going down south based on that from there. So the fingers still go in the direction of the magnetic field. The thumb goes in the direction of the velocity, which is the current, in the direction of the wire. And that's how you can determine which way the magnetic field is going from that. So think through then, if I have this wire like this and all the current is going this way, if I make a loop of the wire and let's say that the current is going this way, I'm going to grab it this way, and everywhere along that loop isn't the magnetic field pointing towards me, because that's the direction that my fingers are pointing. So if I do a double loop here, now my wire is this way. I have twice the wires with the magnetic field going this way. And so I've just made my magnetic field stronger. And that's really the whole idea behind a solenoid, is the more loops that I have here, the stronger that magnetic field is going to be inside of those loops whenever I'm running a current through it. So in summary, remember that we have a wire that creates a magnetic field around it. And either that's going to be a long straight wire, which will be the equation that you see on the left, or it's going to be a loop or a set of loops, which will be the equation that you see on the right, and that's called a solenoid. And then the second part of that is the second right-hand rule is what tells us what direction the field goes around the wire, because our thumb goes in the direction of the current and our fingers will curl in the direction of the magnetic field.